So today we'll talk about stream functions. Stream functions are a very useful concept related to the mass conservation in irrotational flows. So let's remember that for irrotational flows, mass conservation satisfies the equation that the divergence of u is 0. In index notation we would write this dui dxi is 0, and in 2D plane flow, and we'll illustrate stream functions in 2D, in 2D plane flow that would be du dx plus dv dy is 0. Now, for something when the divergent field is 0, we can define a function psi that has following properties. Now define, and that's going to be our stream function. Now define psi, a function of x, y, and t, such that u is d psi dy and v is minus d psi dx. And why would I do that? Because now we can plug this, substitute this into equation 1 here. Then we have d by dx of d psi dy plus d by dy of minus d psi dx, which is d2 psi dx dy minus d2 psi dy dx, and that is 0. So whenever we have an irrotational flow in 2D, the stream function psi will automatically satisfy the mass conservation. Now, let's understand what's the physical interpretation of this stream function. And to get at that, we'll look back to our streamlines, and they are sort of named the same, not by accident. So streamlines, recall streamlines, we had that streamlines are defined by the equation dx over u is dy over v. And now we have these equations here, sub this into streamline equation. Then we get, maybe I should rewrite this, and we'll say that v dx minus u dy is 0. So now if I sub these terms here into this equation down here for v and u, I get d psi dx minus d psi dx dx plus d psi dy dy is 0. Sorry, there's a minus here, right? So really I can just write this as d psi dx dx plus d psi dy dy is 0. But from just the definition of a small element in 2D, we can see that this really is just d psi. So that means d psi is 0 along streamlines, i.e. our stream function psi is constant along streamlines, i.e. streamlines are contours of the stream function. I'll squeeze that in down here, i.e. streamlines are contours of the stream function. So what does that mean when streamlines are contours of the stream function? Let me draw sort of a simple schematic here. We have two stream functions, or sorry, two streamlines. And so these are two streamlines here. And so psi, the stream function always has the same value on each of these stream functions. So let's say this is psi, and this is a adjacent streamline that has some value psi plus d psi. Yeah, so they're fairly close. Now, if we look at the fluxes here, so you might have some flow field, right, and they will be flow field because of the streamlines, the way they are defined, it'll look something like this, because the flow field has to be parallel, yes, tangential to the streamlines. So we can ask, what is the flux between 2 points here? Yeah, what is the flux between two streamlines? So if this is point x, then this would be point x plus dx, and this line here is, this line is dx, and then we have some flux through, and the sum total, basically the integral of all these little velocity flow vectors. And the way we can compute that flux, really, it is the same. It has to be the same as the flux through this by conservation of mass. The fluxes into these two line segments has to be the same as the flux out of the line dx. And the flux into here is simply the minus u times dy, and the flux going into the flowing in the vertical is the vertical component times the line segment perpendicular to that vertical component. So it's v dx. So really v dx plus minus u dy, and that is simply minus d psi dx times dx minus d psi dy times dy equals minus d psi. So what we've done here is basically consider the volume flux between two streamlines. So the physical interpretation here is that the volume flow rate between two streamlines is just the difference between their psi values. And so that means that the volume flow rate between these lines here is always the same. And when the lines are further apart, then the flow is slower because this distance here is wider. And when they're closer together, then the flow has to speed up because the distance is more narrow. So let me just write that out. Okay, finally, let's talk briefly about the vector notation. So in vector notation, we can write that u is nothing but k cross the gradient of our function psi, where k hat is the up vector, right? So k hat is just the up unit vector 0, 0, 1. Let's show that this really is the same as what we found earlier using index notation. So if we have, in general, u is the cross product of two vector fields a and b, then we've shown in index notation that this is just epsilon ijk a j b k from back in the tensor chapter. So let's write that here. We have ui equal epsilon ijk delta j3. That's our k vector, right? It's 0 for j equals 1 and 2, and 1 for j equals 3. And then d psi dxk. So in order to do the contraction between jk and delta j3, we have to permute the indices here. So that means if you permute j and k, you pick up a minus sign. So it's minus epsilon ikj delta j3 delta psi d psi dxk. And now you can contract that, and that just means that the j here turns into a 3. So it's minus epsilon ik3 d psi dxk. And in order to now contract k3 and k, we have to permute again, and so we pick up another minus sign. So now it's epsilon i3k d psi dxk, and that only has two non-zero components, namely when k is 2 and when k is 1, because epsilon is 0 when k is 3. So now we have epsilon i3 1 d psi dx1 plus epsilon i3 2 d psi dx2. And that means, so this is ui, so u1 only leaves us the second term where we have epsilon 1, 3, 2 d psi dx2, and that picks up a minus sign, minus d psi dx2, and u2 leaves you with this term up here. It's just d psi dx1. And that is indeed the same form as we've seen earlier.